Alright everybody, welcome to 4-8 complex numbers. There's a lot to do here, so I'm going to need you to make sure you try each one of these. We're going to go over this a lot in class. This is the only section of this unit. So we're going to make sure that all your questions are answered, but it's important. It's a big deal that you try this stuff on your own. So we're going to look at how to identify, graph, and perform operations with complex numbers, and we're going to find complex number solutions of quadratic equations. That's the big idea. Okay. Let's take a look. In chapter 1, we learned about different subsets of real numbers. Okay, we've been talking about real numbers. The set of numbers itself is a subset of larger set of numbers, the complex numbers. Okay. Curiously, the complex numbers include a number like a in the solve. Its fifth power is itself. Okay. So up here we have it's a multiplication table, and you know all this is true. Anyway, we'll get to that in a second. The big thing in this unit, the complex numbers are based on a number whose square is -1. Okay, there's an imaginary unit, this imaginary number I. Okay, I is equal to the square root of -1. Now this should make a little bit of sense to us because we can't take the square root of -1 and get a real number, but we can get an imaginary number. Okay, so the I stands for imaginary. I squared is -1. So if we look at square root of -1 times the square root of -1, that would, oh, yikes, square root of -1 times the square root of -1 equals -1. So I times I equals -1. Okay. For any positive number a, this is the big deal part right here. For any positive number a, what we're going to do is we're going to factor out the -1. So we just have a left. We can separate those like this, and then the square root of -1 becomes I, and then square root of a is by itself. So the example here is that the square root of -5 is actually I times the square root of 5. That's all that is. Okay? I promise it'll get more complicated. Alright, so how do we write this using an imaginary unit? We separate it like we just said. We take the square root of -1 like we just said. I comes out. Then we have to simplify this and get 3 times the square root of 2, and then this is our final answer. Okay? So let's try these. Okay, let's try these. Got it. Number 1, so we have square root of -12, so that's I times the square root of 12. Okay? Square root of 12 can be simplified to 4 times 3, and square root of 4 is 2. So this is 2I times the square root of 3. B is just really simply the square root, this is I times the square root of 5, or I times the square root of 25, which is 5. So this is just 5I. And C, 7 is a prime number, so this is just I times the square root of 7. Part D asks you why the square root of -64 is not equal to negative times the square root of 64. And that's because this, when we simplify it, we get 8I. Here, we just get -8, and those are not the same number. All right? An imaginary number is any number of the form a plus bi. Okay? A plus bi, that right there. Okay? Where a and b are real numbers, and b is not equal to 0, imaginary numbers and real numbers together make up the set of complex numbers. All right? We can write a complex number in the form a plus bi. That's what we just talked about. That's the real part. That's the imaginary part. If a equals 0 and b does not, the number a plus bi is just a pure imaginary number. And so we'll take a look at what that looks like also. Complex numbers over here, we have real numbers. Over here, we have imaginary numbers. Then over here, we have pure imaginary numbers. That's when there's no real part. There's no a added to it because a was equal to 0. In the complex number plane, the point AB represents the complex number a plus bi. So we have two axes here. This should look a little bit different than what we're used to. Here's the real axis. So that's for the a part. Okay? And then going up and down, we have this imaginary axis. Okay? So that's for the imaginary part. So if we look right here, the absolute value of a complex number is its distance from the origin in the complex plane. So a plus bi, well, we would go over a, so in this case it was 3, okay? So we go over 3 on the real axis, so 1, 2, 3, okay? and then we're going to go down 2i. All right, so we have this. To find the distance of that, okay, the absolute value of that is just a squared plus b squared equals c squared. It's Pythagorean theorem to find that distance right there. Okay, so 3 minus 2i, the absolute value of that is 13. 3 squared is 9. Negative 2i squared, right there, that's 4. And then what we have here is 9 plus 4 is 13, and so the square root of 13. That's how we get that. Looks complicated. I know. We'll have lots of questions, and that's fine. Let's take a look at an example. What are the graph and absolute value of each number? So here's negative 5 plus 3i. So we want to graph it, and we want the absolute value of that. So we go to negative 5 on the real axis. We go up 3i on the imaginary axis. Okay, so this is the graph of it. So far, so good. Okay. Then we're just going to do a squared plus b squared equals c squared. Okay. Negative 5 squared is 25. 3 squared is 9. Okay, 25 plus 9 is 34. So the absolute value of this number is the square root of 34. All right, let's take a look here. 6i, this is part B in blue. All we're doing is graphing 6i. Well, that's there. It has no real value. It's a pure imaginary number. So we just go straight up to 6i. There it is. What's the absolute value of 6i? Well, the a value is 0. 0 squared is 0. The b value is 6. 6 squared is 36. So the square root is 6. So the absolute value of 6i would be 6. All right. What are the graph and absolute value of each of these numbers? So let's take a look. See if you can, try to graph and get the absolute value. And if you can't do one, try to do the other. So if you can't graph it, get the absolute value. If you can't get the absolute value, try and graph it, and then pause the video, and we'll come back and check these against what I have. Okay, pause the video now. All right, so let's take a look. Here's what I got. We'll look at the absolute values first. I got the square root of 26. That's just 5 squared plus 1 squared. Okay, and then it's the square root of that. Here, negative 3 squared is 9. Negative 2 squared is 4. 9 plus 4 is 13. 1 plus 16 is 17. So there's the absolute values of each of these numbers. And then the graph over here, this is over 5 on the real and down 1 on the imaginary. This is left 3 on the real and down 2 on the imaginary. And then this is over 1 and up 4 on the imaginary. So it looks complicated. It's really not too bad. Okay. Let's take a look here. You can define operations on the set of complex numbers so that when you restrict the operations to the subset of real numbers, you get the familiar operations on the real numbers. What does that even mean? So here's what it means. What is each sum or difference? So we want to, this is just combining like terms in the same way if this were like an x or a y or anything like that. So 4 minus 3i plus negative 4 plus 3i is actually just 0. 4 minus 4 is 0. Negative 3ai plus 3i is 0. If we go down here, 5 minus negative 2, so that's 5 plus 2, and then negative 3 minus negative 4i would be 7 minus 7i. So this is literally just combining like terms, old school sort of, algebra 1-ish math. Go ahead and pause the video right here and get some answers, and then we'll take a look at what you guys got there. So pause the video now. All right, so you've unpaused. Let's take a look at A, B, and C, and D. I don't leave a D out. So here's what I got. I got 4 minus I for A. For B, I got negative 2 plus 7i. For C, I got 12i. And for D, I got 18i. All right, if you didn't get those, try and do them again. If you still can't get them, make sure you put a star or something next to it so we know to go over in class. Let's take a look here. When we multiply complex numbers, we would do it the same way we multiply binomials, okay? For the imaginary parts, what we just have to remember is that I squared equals negative 1, okay? I squared equals negative 1. That's the big key to doing these correctly, is that you don't forget this. That's a big deal. Okay, other than that, it's just like FOIL or distributive property or anything else. So here, we got 3i times negative 5, that's negative 15i. 3i times 2i is plus 6i squared, which is actually negative 6. So it becomes that. Here, we can do FOIL, and we're always going to substitute negative 1 for I squared. So go ahead, take a second, use those as a model, try to get 4A, B, and C. 4A, B, and C. Ready, go. Pause the video. All right, so you've unpaused. Let's check your answers against mine. For 4A, I got negative 21. For 4B, I got 23 minus 2I, and it needs to be in that format, guys. Real then imaginary. Real then imaginary. And then 41. Okay? 23 minus 2I and 41 were B and C. Right? In problem 4C, the product is a real number. Number pairs of the form A plus BI and A minus BI are called complex conjugates. Okay? Conjugate is a word. We'll talk a little bit about that. If you're not sure what that means, that's one you're going to want to look up or ask about in class so we understand what the conjugate is. Okay? But complex conjugates are basically, it's the same number or same binomial, but one's a plus and one's a minus. And what happens is the product is a real number. Okay, the product is a real number. Let's take a look at dividing these. Dividing is slightly more complicated just because it's slightly more complicated. Here, the quotient, we have 9 plus 12i over 3i. Okay, so we can do a couple things. We can multiply the numerator and the denominator by the complex conjugate of the denominator. So it's just the opposite of it. Okay, when we do that, up top we get negative 27i minus 36i squared. And on the bottom we have negative 9i squared. So then what we want to do is we can change the I squareds to negative 1s, and then we can simplify. Here I notice that everything is divisible by 9, so I'm left with 4 minus 3i. Over here we're going to multiply by the complex conjugate again, but in this case it's the opposite of this, so plus, and then the same binomial. So we're going to have to FOIL top and bottom. And then at the end, we're going to separate in this so that it is in the form A plus BI. So the real number and then the imaginary number. Okay? These can be kind of work intensive. So if you're doing a lot of work to get to these, it doesn't necessarily mean you're right, but it should feel like a little bit of work. I'm going to set up 5A for you. So 5A, 5 minus 2I over 3 plus 4I. I'm going to multiply that by the complex conjugate. Top and bottom, so 3 minus 4i over 3 minus 4i. Okay, you're going to finish that problem on your own. B, I'll help you set up B also. 4 minus I over 6i. We're going to multiply that one by negative 6i over negative 6i. And we're just multiplying these by a version of 1 that helps us out. If we go over here to part C, we have 8 minus 7i over 8 plus 7i, and you're going to multiply top and bottom there by 8 minus 7i. Okay? Complex conjugate of the denominator. All right, go ahead and pause the video. See if you can get some answers to those. When you unpause, I will have my answers up so you can check them. Go ahead and pause the video now. All right, so you've unpaused. I didn't put my answers up. I lied. Sorry. Here's my answers. 5A. 7/25 minus 26/25 I. Okay. Part B, negative 1/6 minus 2/3 I. That is a god awful too. Okay. And then part C, this one's kind of 15 113ths minus 112 113ths I. If you didn't get those, try them again. If not, I'm happy to take questions on those in class. Okay. All right. Last big thing, or two last example problems. Every quadratic equation has a complex number solution that sometimes are real numbers. Some quadratic equations have pure imaginary solutions. So we're working this problem right here, and we've talked about when the discriminant is negative, we said that there are no real solutions. The key there is that there's no real solutions. There are imaginary solutions. So this problem, for example, we get 2x squared equals negative 32. Divide by 2 and we get square root of 16, or negative 16. We take the square root of both sides, and we have plus or minus the square root of negative 16. Well, now that we know what imaginary numbers are, we can actually take the square root of that and get plus or minus 4i. Okay, let's take a look at 6a. Here, we're going to solve, so we get 5x squared equals negative 20. we get x squared equals negative 4. When we take the square root of both sides, let me move this over so you can see it. When we take the square root of both sides, we get x equals plus or minus the square root of 4. So x equals, and again, we have to understand this, plus or minus the square root of 4, it's negative 4, sorry. Plus or minus the square root of negative 4, I'm going to erase that. That's just, goodness gracious. That's the square root of negative 4 is 2i. Okay? So this is x equals plus or minus 2i. See if you can pause it and get the answer to part B on your own. Pause it now. Part B was a little bit easier because 15, there is no square root of 15. Okay? So there's nothing to simplify. X equals, pay no attention to that, x equals plus or minus I times the square root of 15. Okay? Problem 7 is just a quadratic formula, but when we have the quadratic formula and we have negative numbers, I is going to come into play again. Okay? So we're going to work these out using the quadratic formula, and then we're going to have some imaginary answers. So let's take a look at how this happens on number 7. All right, so let's look at number 7. Part A and B, and I'm going to do the setup for those for you, and then you are going to try and finish them yourself. The important thing when using the quadratic formula is to make sure that the equations are both set equal to 0, which they both are. Okay. Then we want to make sure we understand what the A, B, and C equal are. What the A, B, and C are. So A equals 3, B equals negative 1, C equals 2 for 7A, and we'll even do B while we're here. A equals 1, B equals negative 4, and C equals 5. So we're going to use the quadratic formula, which we worked with on the first part of Unit 4 that we did, or Chapter 4. So we're going to set up our equations. So x equals the opposite of b, so that's 1, plus or minus the square root of b squared, which is 1, minus 4 times a times c. Well, 4 times 3 is 12, and 12 times 2 is 24. Okay? We have that, and then it's all over 2a, which is 6. Okay? So then we're just going to start simplifying as best we can. All right, we have x equals 1 plus or minus the square root of negative 23 over 6. Okay, from there that's where we need to remember that we can factor negative 23 into this equals the square root of negative 23 equals the square root of negative 1 times 23, which is I times the square root of 23. Okay? So when we have that, we have, and it might also make it easier if we split these two up. So let's do that first. Let's say 1 over 6 plus or minus the square root of negative 23 over 6. Because remember, we always want these in the form of a plus bi. Then all I have to do is simplify this radical right here and make that I times the square root of 23 over 6. And as ugly as that is, that's your answer. You have no right to judge, okay? Everybody's a snowflake and they're all beautiful in their mother's eyes. So that's the answer. Go ahead and pause the video right here. Try to get an answer for part B, and then when you unpause, I will give you that answer, okay? Go ahead and pause the video now. Okay, you've unpaused. The answer for part B is 2 plus or minus I. So that one was really ugly. That one's really not. If you didn't get the same answer I got, go through the problem again, see if you can get it. If you still can't get it, make sure you put a star, a heart, or an asterisk, or something by that so we can go over it in class. I'd like to thank my 6th period Algebra 1 class for being a part of this last section of the video. They were great. They were very quiet. You guys didn't even know they were there until right now. Say hi, guys. All right, don't get that's ridiculous. All right, bye. See you next time.